A black hole is not invisible in the ordinary sense of being merely dim. It is invisible for a harder reason. At the boundary called the event horizon, gravity becomes so extreme that no signal that has crossed inward can return outward. Not visible light, not X-rays, not radio waves. NASA describes black holes as effectively invisible for exactly this reason, and that single fact changes the way astronomers have to study them. They do not wait to see the black hole itself shining in space. They look for what the black hole does to nearby gas, nearby stars, and even to light passing close by. That is the central paradox of this subject. The object itself withholds light, yet its gravity can reorganize an entire region of space around it and leave behind evidence too strong to ignore. That difference matters because many dark things in the universe are still visible in principle. A cold planet reflects a little light. A dead star may glow faintly. A cloud of dust can block light and still announce its presence by silhouette. A black hole is different. Outside the event horizon, light can still orbit, bend, scatter, and escape if it has the right path. But once anything goes inside that boundary, the route outward is gone from the structure of space-time itself. This is why the event horizon is so important. It is not a hard shell and not a material surface like the surface of Earth or the Sun. NASA describes it as a boundary, a limit, the point beyond which escape no longer exists. That is why black in black hole does not simply mean dark-colored. It means hidden by a one-way geometry. The path to this idea began long before anyone had evidence for a real black hole. In 1916, soon after Albert Einstein published general relativity, Karl Schwarzschild found an exact solution describing how space and time behave around a compact, non-rotating mass. That solution revealed a critical radius. If enough mass is squeezed inside that limit, escape becomes impossible. Later work expanded the picture to rotating black holes as well, because real collapsed stars and real galactic centers are not expected to sit perfectly still. What matters for this first step is that invisibility was not added as a dramatic extra. It came directly from the mathematics of gravity. If gravity curves space-time deeply enough, every future path inside the horizon points inward. Light does not fail because it is weak. Light fails because there is no outward direction left for it to take. That can sound abstract until we compare it with a more familiar idea: escape velocity. On Earth, a rocket must climb to about 11 kilometers per second to break free of our planet's gravity. ESA explains that for a black hole, the escape velocity exceeds the speed of light. Since nothing with mass can outrun light, and light itself is already the speed limit of the universe, the result is final. There is no stronger flashlight that can solve the problem. No brighter signal. No clever angle of emission once the horizon has been crossed. This is why the center of a black hole cannot simply be illuminated if our telescopes improve enough. Better instruments help us study the edge, the feeding disk, the jets, the surrounding stars, the warped background light. They do not turn the interior transparent. So how did astronomers become confident that black holes are real if the defining object refuses to send back light? The answer is that nature rarely leaves a black hole alone. Gas falls in. Companion stars get tugged off balance. Matter heats as it spirals inward, rubbing and colliding in an accretion disk until it reaches millions of degrees. NASA notes that this hot material can shine strongly in X-rays just outside the event horizon, which is why some of the first convincing black hole candidates were found not by seeing the hole itself, but by seeing matter in distress around it. The classic case is Cygnus X1, identified in 1971 as the first black hole ever discovered in this way. Astronomers did not observe a black sphere with a label on it. They measured a compact object in a binary system whose mass was too high for a neutron star, while the surrounding material blazed in X-rays as it fell inward. The black hole stayed dark. Its surroundings did the speaking. This method of detection is the foundation of black hole astronomy. It is also one reason black holes are so scientifically rich. A dark object by itself might be almost impossible to study. A dark object that bends star orbits, heats gas, launches jets, and reshapes whole galactic nuclei becomes measurable from many angles at once. Near the center of the Milky Way, for example, astronomers spent years tracking stars, whipping around an apparently empty location. Their orbits demanded that about 4.3 million suns worth of mass be packed into a region extremely small by galactic standards. NASA notes that this is Sagittarius A star, the supermassive black hole at our galaxy's center. Again, the logic is important. The black hole was not first accepted because someone saw its body. It was accepted because its gravity controlled the motion of stars over long periods in a way no ordinary cluster of faint objects could easily explain. That brings us to a moment many people remember, the first black hole image. In April 2019, the Event Horizon Telescope collaboration released the image of the black hole in Messier 87. In May 2022, they released the first image of Sagittarius A star. At first glance, this seems to overturn everything just said. If black holes are invisible, how did we photograph one? The answer is precise. The Event Horizon Telescope explains that this is not a classical photograph of the black hole interior. It is an image of radio emission from hot material around it, together with the dark shadow produced because the black hole captures light and strongly warps the paths of light near the horizon. In other words, even our most famous black hole images are images of the neighborhood and of the silhouette effect, not a bright portrait of the hidden interior. The whole remains true to its nature. We see the borderland where light still struggles, not the region from which no light returns. The invisibility becomes even more striking when we remember that black holes are not always feeding. Some are active and easy to notice because gas is pouring in. Others are almost dormant. NASA notes that Sagittarius A star is much less luminous than many other galactic black holes because it is not currently consuming large amounts of nearby material. ESA reported in 2024 that Gaia data revealed a stellar origin black hole with nearly 33 times the mass of the Sun, less than 2,000 light-years away. It had remained hidden because it was not putting on a bright accretion display. That is an important correction to a common mental picture. Black holes are not always violent cosmic vacuum cleaners pulling everything inward at once. Many spend long spans in relative inactivity, revealing themselves only through subtle gravitational influence on a companion star or through careful mapping of motion. There is another layer here that makes black holes scientifically useful rather than merely mysterious. Because they do not emit direct light from within the horizon, every observation forces astronomers to think in terms of cause and effect. Why is the nearby gas this hot? Why is the orbit of that star so fast? Why is a jet emerging from the galactic core? Why does the background light bend into arcs and rings? Black holes train astronomy to work like a forensic science. The missing object is reconstructed from pressure, heat, motion, timing, polarization, and warped geometry. That is why this field has grown through many tools at once: X-ray observatories, radio arrays, infrared telescopes, and long-term stellar tracking. Each measures a consequence. The hidden source is inferred with increasing precision, and yet the central fact remains simple. A black hole is invisible because the event horizon is not just a place where light grows dim, but a place where return becomes impossible. That is why NASA can describe black holes as effectively invisible while still studying them so closely. The work is possible because the universe does not hide these objects perfectly. Matter falls inward. Light bends around them. Stars move under their gravity. Space near them carries clear signs of their presence. So the darkness of a black hole is not the end of observation. It marks the beginning of a different kind of observation, one that depends less on direct sight and more on tracing the physical consequences written around a boundary beyond which light can no longer return. If no light can escape, what exactly is the event horizon, and where does that one-way limit truly begin? When the first black hole image was released in April 2019, many people understandably thought astronomers had finally taken a direct photograph of the black hole itself. But that is not quite what happened. The image of Messier 87 star, usually written M87 star, did not show the hidden interior of a black hole. It showed a bright ring of emission from extremely hot gas moving around it, together with a dark central region created because strong gravity bends light and captures part of it near the event horizon. That dark center is often called the black hole's shadow. In May 2022, the Event Horizon Telescope released a similar result for Sagittarius A star, the supermassive black hole at the center of the Milky Way. The same basic idea applied there as well. These were not ordinary portraits of invisible objects suddenly made visible. They were images of light from matter around black holes, shaped into a ring-like structure by gravity so intense that it changes the very paths light can take. That distinction matters because a black hole does not become visible simply because a telescope becomes powerful enough. A telescope can collect light only if light reaches it. The event horizon marks the boundary beyond which outward escape is no longer possible. So, the Event Horizon Telescope, or EHT, was never trying to photograph some glowing material surface hidden inside the black hole. It was built to study the region just outside that boundary, where infalling gas becomes very hot, and where light is bent, boosted, delayed, and in some cases swallowed altogether. That is why NASA describes the historic image as the black hole being outlined by emission from hot gas swirling around it. The black hole stays dark. The surrounding plasma gives astronomers something to measure. M87 star was the first target for good physical reasons. It sits in the giant elliptical galaxy Messier 87, about 55 million light-years from Earth according to EHT and ESO material, though many popular summaries round that to about 53 or 55 million. Its black hole has a mass of about 6.5 billion suns. That is vastly larger than the black hole in our own galaxy. Even though M87 star is much farther away than Sagittarius A star, its enormous size makes its apparent shadow on the sky large enough to be resolved by a planet-sized virtual telescope. EHT and ESO both note that M87 star and Sagittarius A star end up appearing surprisingly similar in angular size from Earth for this reason. One is much bigger, the other is much closer. Sagittarius A star, by contrast, lies at the center of the Milky Way, about 26,000 to 27,000 light-years away, with a mass of roughly 4.3 million suns. That sounds enormous, and it is, but compared with M87 star, it is much smaller. NASA describes Sagittarius A star as containing the equivalent mass of about 4.3 million suns and lying about 26,000 light-years away. The EHT and ESO comparisons emphasize that, despite this huge difference in mass, the two black holes appear roughly the same size on the sky because of their different distances from us. This is one of the reasons both became prime targets for the EHT project. The Event Horizon Telescope itself is not one physical dish. It is a global network of radio observatories working together using very long baseline interferometry. In practice, astronomers combine signals from telescopes spread across Earth, so the network acts like a single virtual telescope with an effective diameter comparable to our planet. That is necessary because the structures near a black hole's event horizon are unimaginably small on the sky. EHT material explains that the array observed at a wavelength of about 1.3 millimeters, which is short enough to probe close to the horizon while still penetrating some of the obscuring material along the way. This is why the famous black hole images are not visible light photographs like an ordinary camera shot. They are reconstructions from radio data collected at multiple sites and combined with careful modeling and imaging algorithms. That raises a practical point many people miss. The orange ring image is not orange because black holes glow orange. The EHT data were taken in radio wavelengths, not in ordinary visible color. The colors in the public images are chosen to represent intensity in a clear way for human viewers. What matters scientifically is the structure, a bright asymmetric ring surrounding a darker central depression. EHT described the M87 star result as a bright crescent formed by hot plasma swirling around the black hole, together with a dark shadow region. That asymmetry is not decorative. It tells astronomers about motion, viewing angle, and relativistic effects. Gas moving partly toward us can appear brighter because its radiation is boosted, while gas on the opposite side can appear dimmer. So what exactly is the shadow? It is not the event horizon itself, drawn as a neat circle. The dark region in the image is larger than the event horizon because gravity near the black hole strongly bends light. Some photons that pass near the black hole are captured. Others loop around before escaping. The result is a dark central area against the glowing background of surrounding plasma. In simple terms, the shadow is the imprint of paths of light that do not make it back out to us. It is therefore a gravitational silhouette, not a direct look into the interior. EHT results for both M87 star and Sagittarius A star consistently describe a ring-like structure with a central depression, matching what general relativity predicts for light propagating near a black hole. This is why the M87 star image was so important. It gave astronomers the first direct event horizon scale view of a supermassive black hole environment and showed a shadow size consistent with Einstein's theory. NASA described the image as historic, not because the black hole itself had suddenly become bright, but because the boundary scale structure around it could finally be resolved. Later EHT work added polarization measurements, showing magnetic fields near the edge of M87 star and helping researchers understand how this galaxy launches its famous jet. That extended the meaning of the original image. The ring was not just a symbol. It became a working laboratory for studying plasma flow, magnetic fields, and jet launching near a black hole. Sagittarius A star was in some ways a harder target, even though it is much closer. The reason is time. The gas around Sagittarius A star changes brightness and structure much faster than the gas around M87 star because the Milky Way's central black hole is far less massive. Smaller black holes have shorter characteristic timescales near the horizon. NASA's educational explanation notes that material around M87 star can take days to weeks to change substantially, while material around Sagittarius A star can vary on timescales of minutes. That means astronomers were not photographing a calm, steady ring. They were combining data from a rapidly changing source and then extracting the persistent ring-like structure hidden inside that variability. That helps explain why the Sagittarius A star image looks blurrier and more challenging to interpret than the first public image of M87 star. The source itself was more restless while the observations were being made. Even so, the final EHT result again showed a bright ring with a dark central region, consistent with a supermassive black hole at the center of our galaxy. The image was not a coincidence and not a decorative artist's impression. It was the result of comparing many models and many reconstructions against the data to find the structure that kept appearing. There is another misconception worth clearing away. People often hear first image of a black hole and imagine that before 2019 astronomers had only indirect hints. In reality, the evidence for black holes had been accumulating for decades through stellar orbits, X-ray binaries, jets, and galactic nuclei. What the EHT added was not the first belief that black holes exist, but the first ability to image structure on the scale of the event horizon itself. That is a more precise and more impressive claim. It moved the field from inference alone to horizon-scale imaging. Seen this way, the famous images become even more interesting. They are not simple snapshots of darkness. They are maps of how gravity rearranges light near the most extreme objects known. The ring marks where hot plasma is radiating. The dark center marks where light paths are being lost from our view. The uneven brightness carries information about motion and orientation. The polarization results add clues about magnetic fields. A single image, then, is already packed with physics. It tells us about space-time geometry, plasma behavior, relativistic beaming, and the scale of the black hole's influence. So if someone asks what the Event Horizon Telescope really photographed, The clearest answer is this. It recorded radiation from hot material moving just outside a black hole, and from that light, astronomers revealed a dark shadow formed because the black hole's gravity bends light and captures part of it. For M87 star, that structure came from a black hole about 55 million light-years away in the galaxy Messier 87. For Sagittarius A star, it came from the black hole at the center of the Milky Way, about 26,000 light-years from Earth. In both cases, the black hole itself remained hidden in the strict sense, because nothing from inside the event horizon was being seen. And that is exactly why those images matter so much. They show how close modern astronomy can come to an invisible object without ever violating the rule that makes it invisible in the first place. Why does the brightest region around a black hole make the black hole look even darker? A black hole becomes most dramatic, not when it is alone, but when it is surrounded by matter bright enough to expose what cannot be seen. That is the strange visual logic of black hole astronomy. The hole itself does not shine from inside the event horizon, yet gas outside that boundary can be heated to such extreme temperatures that it becomes one of the brightest sources in the universe in X-rays and other high-energy radiation. NASA explains that when matter forms an accretion disk around a black hole, particles in the disk accelerate, collide, and heat to millions of degrees, producing detectable X-rays. ESA describes the same process in similar terms. Gas and dust swallowed by black holes are heated to millions of degrees Kelvin, and their immediate surroundings emit strongly in X-rays. That is why the darkness in the middle can look even deeper. The brighter the gas around the hole becomes, the more sharply the missing light at the center stands out. This is the physics behind the title of a published talk by Kip Thorne, listed by the California Institute of Technology as Black Holes, the most luminous objects in the universe, but no light. The phrase sounds contradictory at first, but the contradiction dissolves once the roles are separated properly. The black hole itself does not send light outward from inside the horizon. The luminosity comes from the environment just outside, where gravity has not yet trapped everything, but has already accelerated gas to tremendous speeds and temperatures. So the bright region is not a failure of the black hole idea. It is one of the clearest confirmations of it. To see why, it helps to start with falling matter. Gas drifting near a black hole does not usually plunge straight inward in a clean line. It tends to carry some sideways motion, and that angular momentum forces the material into a flattened, rotating structure called an accretion disk. As the gas circles inward, neighboring layers rub, collide, and exchange energy. Friction, turbulence, and magnetic effects convert gravitational energy into heat. By the time the gas reaches the inner part of the disk, it can be so hot that it glows not mainly in visible light, but in ultraviolet and X-rays. NASA's Black Hole Explainer says this heating to millions of degrees is exactly why X-ray telescopes can detect otherwise invisible black holes in binary systems. That means some black holes first entered astronomy not as dark circles, but as violent X-ray sources. In a binary system, if a normal star orbits close enough to a black hole, the black hole's gravity can strip gas from the star's outer layers. That stolen gas spirals inward, forming a hot accretion disk. NASA notes that this process produces detectable X-rays, while ESA explains that the X-ray output grows stronger as more matter piles up near the hole. So when astronomers detect an intense X-ray source in a system where the compact object itself cannot be seen directly, they are often reading the signature of matter being heated on the way down. The light belongs to the doomed gas. The darkness belongs to the destination. This is why the brightest region around a black hole can make the hole look darker rather than brighter. Human vision, and image processing more generally, depends on contrast. A dark region against a dim background may be hard to notice. The same dark region against a blazing background becomes unmistakable. In black hole images, the accretion flow or hot plasma ring provides that bright background. The central shadow appears darker because nearby radiation is intense and because strong gravity captures or redirects some of the light that would otherwise have filled in the center. Event Horizon Telescope descriptions of M87 star repeatedly refer to a bright crescent or ring surrounding a deep central depression, the shadow of the black hole. The central darkness is not painted there by empty space alone. It is sharpened by the light around it. The result can seem almost theatrical, but the mechanism is concrete. Near the black hole, gravity bends light paths so strongly that some photons are captured and others are forced into curved trajectories. At the same time, the gas orbiting nearby is hot and luminous. The combination produces a bright ring-like structure and a darker center. That center is not a photograph of the event horizon as a sharp physical surface. It is the visible consequence of light being removed from certain directions by extreme gravity. The brighter the surrounding plasma, the easier that absence becomes to recognize. This effect is especially important because black holes themselves do not always advertise their presence. A dormant black hole with little gas nearby can remain difficult to detect. But once matter begins to fall in, the region outside the horizon becomes an engine for converting gravity into radiation with extraordinary efficiency. ESA's Athena Science Overview notes that the immediate surroundings of black holes emit much of their energy in X-rays because accreted material is heated to millions of degrees. In other words, the black hole can sit inside a region of fierce brightness while remaining internally unseen. The source of the spectacle is not escape from inside the hole, but the final struggle of matter that has not crossed the horizon yet. This helps explain why black hole environments are often described as more informative than the black holes themselves. Astronomers do not study the hidden interior directly. They study the heating, the motion, the magnetic fields, the polarization of light, and the changing brightness of the surrounding plasma. Event Horizon Telescope results on M87 star showed not only the ring and shadow, but later also the polarization pattern, which traced strong magnetic fields near the edge of the black hole. The collaboration explained that the plasma surrounding black holes is threaded with magnetic fields, and these fields help control how matter moves and how jets may be launched. So the luminous environment is not just decoration. It is the measurable laboratory where the physics becomes visible. There is another reason the brightness matters. It tells us where the energy really comes from. A common mental image is that black holes somehow generate light from darkness itself. That is not the right picture for ordinary accreting black holes. The energy comes from matter losing gravitational potential energy as it falls inward. The closer the gas gets, the faster it moves. The faster it moves, the more violently it collides, and the hotter it becomes. By the inner disk, conditions can be extreme enough for strong X-ray emission, and in active galactic nuclei, the total output can influence an entire galaxy. NASA's Active Galactic Nuclei Explainer describes such systems as active supermassive black holes that emit bright jets and winds and shape their galaxies. The black hole does not shine by breaking its own rule. The infalling matter shines because gravity is extracting energy from its descent. That is why the phrase glowing black hole can be misleading if taken too literally. What glows is usually the accretion disk, the corona above the disk, or jets launched from the surrounding magnetized plasma. NASA's nicer explanation of X-ray echoes from a newly discovered black hole points out that the inner edge of the accretion disk can lie very close to the event horizon, while the corona is compact and produces strong X-rays that then reflect from the disk. ESA's XMM Newton science pages likewise describe how matter accreting around a black hole emits X-rays and illuminates nearby matter before disappearing beyond the event horizon. So, even when the environment is brilliant, the central rule remains intact. Once matter or light crosses the horizon, the outward report ends. The contrast between bright surroundings and dark center also explains why black hole images can look more dramatic than images of many luminous stars. A star shines across its visible surface, so brightness is spread over a disk. A black hole system can concentrate radiation into a narrow ring or hot inner flow surrounding a dark depression. That geometry exaggerates the sense of missing light. Event Horizon Telescope material on the wobbling shadow of M87 star described a bright crescent formed by hot plasma swirling around the hole and a dark central region. The structure remained persistent across years of observations, even though details in the brightness changed. The darkness looked stable not because nothing was happening, but because the underlying geometry imposed a recurring shape on the light around it. There is also a scale difference worth noticing. In stellar mass black hole binaries, the key radiation often arrives as X-rays from hot inner disks. In supermassive black holes, especially those in active galactic nuclei, the full environment can include accretion disks, hot coronas, broad emission regions, and giant jets spanning immense distances. Yet the principle stays the same across those scales. The hole itself remains dark in the direct sense, while the matter around it can be dazzling. NASA's NuSTAR team notes that high-energy X-rays can even reveal black holes hidden behind thick gas and dust clouds, because visible light often cannot get through while the X-rays can. That tells us something important. The most useful signal from a black hole may not be ordinary light at all, but harder radiation produced in its extreme surroundings. The visual picture of black holes becomes more powerful here, not less mysterious. The bright disk does not contradict the black hole's darkness. It frames it. The X-rays do not come from inside the event horizon. They mark the last energetic region, where matter is still outside and still able to radiate. The glowing plasma does not make the black hole visible in the ordinary sense. It makes the missing center stand out more sharply. That is why some of the most luminous environments in the universe can produce the most striking images of absence. Could a black hole pass right through the Milky Way without anyone seeing it? Yes. Under the right conditions, a black hole could move through the Milky Way and remain extraordinarily difficult to spot. That is not because it becomes less massive, and not because its gravity stops working. It is because an isolated black hole may produce almost no light of its own. If there is no companion star feeding it, no hot accretion disk, and no strong jet, then the usual bright warnings disappear. What remains is gravity alone. NASA's Hubble team put the point very plainly in 2022. Black holes do not emit or reflect light, so they cannot be directly observed, but their presence can be measured through the way they distort the light of a background star during a microlensing event. That possibility is more unsettling when the scale is added. In the same NASA report, astronomers estimated that roughly 100 million black holes may roam among the stars of the Milky Way. Most of them are expected to be the crushed remnants of massive stars that exploded as supernovae. If the explosion was not perfectly symmetric, the newborn black hole could receive a kick and travel through interstellar space rather than staying tied to a bright binary system. NASA described them as rare descendants of stars, at least about 20 times the Sun's mass, set loose after collapse and explosion. So the thought is not fantasy. Our galaxy may contain a vast hidden population of these objects, most of them dark, unless chance geometry briefly exposes one. The method that can reveal such a traveler is gravitational microlensing. When a compact object passes almost exactly in front of a background star, its gravity bends the star's light. To an observer on Earth, the background star can brighten for a while, not because the star itself changed, but because space-time along the line of sight was warped by the unseen foreground object. NASA explains that telescopes monitoring crowded star fields toward the galactic bulge look for exactly this temporary brightening. Hubble then follows the most interesting cases and measures something even more delicate: the tiny shift in the apparent position of the star on the sky. That positional wobble is called astrometric microlensing, and it gives astronomers far more leverage on the mass of the invisible lens. This distinction is crucial. An ordinary microlensing light curve can tell astronomers that something massive crossed the line of sight, but it does not always reveal whether the lens was a star, a white dwarf, a neutron star, or a black hole. The extra astrometric shift helps break that ambiguity. A 2025 monthly notices of the Royal Astronomical Society paper reviewing the same event explains that combining photometric microlensing with milliarc second level astrometry reduces the degeneracy between lens, mass, distance, and relative motion. That is why isolated black holes are so hard to find, and why they are scientifically valuable once found. Their darkness hides them from ordinary surveys, and only a brief, precise distortion of another star's light can betray them. The best-known case is OGLE2011b LG0462, also called MOA2011b LG191. The event was first noticed in 2011 toward the crowded stellar fields of the galactic bulge. NASA's 2022 Hubble release said the background star brightened beginning in August 2011 and then faded back to normal as the unseen foreground object moved on. Hubble's follow-up over 6 years allowed astronomers to measure both the brightness amplification and the tiny astrometric deflection. From that, the Hubble-led team argued they had found direct evidence for a lone black hole drifting through interstellar space. NASA placed it about 5,000 light-years away in the Carina Sagittarius spiral arm of the Milky Way, That announcement got attention because it was not a black hole in a binary, not a black hole in a galactic nucleus, and not a black hole found through gravitational waves from a merger. It was something darker and more solitary, a compact object crossing the galaxy without a bright partner to reveal it. NASA noted that until then, stellar mass black hole masses had generally been measured either statistically in binary star systems through X-rays and orbital effects, or in other galaxies through merger signals. An isolated black hole would be different. It would be a direct look at a population that theory long expected but observation had struggled to catch. Even so, the story did not end with a single clean answer. In 2022, another team analyzing nearly the same event argued for a lower mass range that allowed either a low-mass black hole or a neutron star. That disagreement mattered because the whole point was to decide whether the invisible lens had crossed the threshold into black hole territory. Later reanalyses moved the mass upward. The 2025 Monthly Notices paper summarizes that early split clearly. One solution gave about 7.1 solar masses, while alternative analyses initially allowed values as low as roughly 2 to 4 solar masses. Subsequent reanalyses brought the estimates into better agreement at around 6 to nearly 8 solar masses, which rules out a neutron star more comfortably. That makes the careful wording important. In 2022, NASA and Hubble reported the first direct evidence for a lone black hole roaming the Milky Way. Since then, follow-up analyses have generally strengthened the black hole interpretation rather than weakening it, although the path there involved real technical disagreement about how to reduce and interpret extremely subtle Hubble astrometry. The current picture is stronger than the first headlines, not weaker. The same 2025 paper calls OGLE2011BLG0462 the most convincing case for the first discovered stellar mass isolated black hole in the Milky Way. One reason this event is so persuasive is that the lens stayed dark. That absence matters. If a normal star had caused the microlensing, astronomers might have expected to detect light from the lens itself once the geometry changed enough to separate source and lens contributions. But this object did not reveal such light. NASA's explanation emphasized that because a black hole does not emit or reflect light, it cannot be photographed directly. Only its gravitational thumbprint can be measured. The Monthly Notices paper adds another supporting point. Deep Chandra observations placed a very low upper limit on any X-ray luminosity from the object, reinforcing the picture of a dark, isolated remnant rather than a bright, accreting system. That last point helps answer the central fear in your title. Could a black hole pass through the Milky Way without anyone seeing it? Yes, if seeing means detecting emitted light directly. A truly isolated black hole could pass through ordinary interstellar space with very little electromagnetic drama. It would not light up like the black holes in movie posters. It might not glow in X-rays at all. It might not have a disk. It might leave no obvious visual trace until, by chance, it aligns with a background star closely enough to lens that star's light. In that sense, the galaxy may be full of massive objects that are not hidden because they are far away, but because they are optically silent. There is also a deeper unease in the numbers. NASA's release says the candidate black hole from the Hubble study was moving at about 100,000 miles per hour, or about 160,000 kilometers per hour, through the galaxy. It also notes that the nearest isolated stellar mass black hole to Earth might be as close as about 80 light-years, though that is a statistical estimate, not a confirmed nearby object. 80 light-years is not close enough to threaten the solar system, but it is close enough to change the emotional scale of the subject. The Milky Way is not just a map of luminous stars. It may also be a much darker map of collapsed remnants moving between them, mostly unnoticed. This does not mean stray black holes are likely to wander into the inner solar system without warning. Space is vast, and the average spacing between stars is enormous compared with the size of planetary orbits. The real point is observational, not apocalyptic. If an isolated black hole does not actively accrete matter, then astronomy must find it by geometry and patience rather than by brightness. That is why microlensing surveys matter so much. NASA noted that only 1 in a few hundred microlensing events is predicted to be caused by an isolated black hole, making the search a genuine needle-in-a-haystack problem. The future of this search may be much richer. NASA's 2022 report said the Nancy Grace Roman Space Telescope is expected to discover several thousand microlensing events and measure deflections with very high accuracy, opening the possibility of finding many more isolated black holes. The 2023 and 2025 follow-up studies echo that expectation. Roman should be able to measure large samples of isolated black hole masses through microlensing, which would help map the hidden remnant population of the Milky Way and improve models of massive star evolution and black hole formation. So the uneasy idea at the center of this part is also scientifically productive. The very fact that black holes can roam unseen forces astronomy to invent better ways of measuring gravity itself. So the answer is not only yes, but yes in a very specific way. A black hole could cross the Milky Way without appearing as a bright object, without shining, and without announcing itself through ordinary light. But it would still carry gravity with it. And if it passed in front of a distant background star, then for a short time that star could brighten, shift, and reveal the invisible traveler moving between us and the galactic background. That is why the isolated black hole candidate reported with Hubble data in 2022 mattered so much. It showed that even when a black hole produces no bright glow of its own, space-time around it can still leave enough evidence for patient observers to catch it in motion. If black holes hide all their light, how did Andrea Ghez prove one is sitting in our galaxy? No one watched the black hole at the center of the Milky Way shine into view. No telescope opened a direct window onto its interior. What Andrea Ghez and her collaborators did was more demanding than that. They watched stars. Year after year, they measured tiny points of infrared light crowded into the dusty core of our galaxy and asked a plain physical question. What kind of hidden mass could force those stars to move this fast, turn this sharply, and complete such tight orbits in such a small region of space? The answer that survived the measurements was severe. At the galactic center, an invisible, extremely massive compact object was controlling the motion, and the Nobel Committee stated in 2020 that a supermassive black hole is the only currently known explanation. That conclusion did not arrive in a single night. It was built over decades. Since the 1990s, The teams led by Andrea Ghez in the United States and Reinhard Genzel in Europe developed and refined methods for tracking the motions of stars near Sagittarius A star, the radio source at the center of the Milky Way. The Nobel materials described their work in simple terms. Because black holes themselves do not let light escape, they must be studied through the radiation and movement of nearby objects. That is exactly what these teams did. They did not try to make the hidden object glow. They measured what gravity around it was doing to everything nearby. The setting made the work unusually difficult. The center of the Milky Way is buried behind thick clouds of interstellar dust, which block much of the visible light coming from that region. So the observations had to be done largely in infrared, where the dust becomes less obstructive. UCLA's Galactic Center Group explains that images at about 2.2 microns from the W.M. Keck telescopes were used to track stellar orbits around Sagittarius A star. That already tells us something important about how this proof was assembled. It was not built from one spectacular image alone. It was built from repeated high-resolution measurements, careful alignment, and long patience in a part of the sky where stars crowd together and dust complicates every observation. The breakthrough came from motion. In everyday life, mass often reveals itself by resisting change or by pulling on something else. In astronomy, the same principle becomes sharper because orbits can be measured. If a star moves in a wide, lazy path, the central mass may be modest or spread out. If a star whips around a tiny region at enormous speed, then the mass controlling it must be both large and highly concentrated. That was the logic at the center of Ghez's work. By measuring the positions and velocities of stars near Sagittarius A star, her team could infer the mass and compactness of the hidden object without needing to see it directly. One star became especially important. In Europe, it is commonly called S2. In UCLA work, the same star is often called S0-2. This star follows a tight orbit around the galactic center and became one of the most powerful tracers of the invisible mass there. ESO reported that both Genzel's and Ghez's groups accurately traced this orbit, and that after 16 years of tracking stars around Sagittarius A star, the observations had delivered the best empirical evidence that a supermassive black hole exists at the center of our galaxy. UCLA reported in 2012 that another fast star in the same region completed an orbit in only about 11.5 years, showing that the inner galactic center is a place of astonishing speeds and strong gravity. What made these orbits so persuasive was not only that the stars moved quickly, but that they curved around an apparently empty point. If there had been a cluster of ordinary faint stars, dead stellar remnants, or some puffed-out cloud of matter at the center, the orbits would not have looked the same over time. A distributed mass produces a different gravitational field from one concentrated into a tiny region. The Nobel Committee's summary states that an invisible and extremely heavy object governs the star's orbits at the center of the Milky Way, and that a supermassive black hole is the only currently known explanation. In other words, the measurements did more than say, something heavy is there. They constrained how small that heavy thing had to be. By 2008, the case had become especially strong. ESO's announcement on the long-term galactic center study said the stellar orbits showed that the central mass concentration of about 4 million solar masses must be a black hole beyond any reasonable doubt. That phrase is strong but it rests on a physical comparison. 4 million suns is an enormous mass. If that mass was spread across a star cluster rather than packed into a compact object, the cluster would be unstable under the measured conditions. The stars near the center were moving as though they were circling a single dominant mass confined to a very small volume. Andrea Ghez's contribution was therefore not a matter of rhetoric or broad interpretation. It was observational discipline. UCLA's Galactic Center Group notes that for more than 2 decades, she collected data on stars orbiting the black hole and used those motions to test the laws of physics near a supermassive black hole. That long time span mattered because orbital proof is cumulative. A single partial arc on the sky may hint at a central mass, but complete or near-complete orbits transform suggestion into measurement. The period, shape, closest approach, and speed of a star like S0-2 all feed into the estimate of the hidden object's mass and distance. There is also a technical reason the result became more convincing over time. Better instruments sharpened the positions of the stars. ESO notes that developments and infrastructure upgrades at Paranal enabled increasingly accurate measurements of S2, especially during its close approach in May 2018. With better astrometry and spectroscopy, astronomers could do more than trace a rough orbit. They could measure how fast the star was moving along our line of sight and across the sky, then compare the motion with the predictions of gravity around a supermassive black hole. This is where the story becomes even more satisfying. The observations did not stop at proving a compact object was present. They also reached the stage of testing general relativity in the strong gravitational field near Sagittarius A star. ESO reported in 2021 that stars on close orbits around Sagittarius A star follow paths exactly as predicted by general relativity for objects moving around a black hole of about 4.30 million times the mass of the Sun. That number matters because it is not just a dramatic label. It is a measured property tied to orbital data. So how did Ghez prove a black hole is sitting in our galaxy if black holes hide all their light? By refusing to ask the wrong thing of the universe. She did not ask the black hole to announce itself with direct light from inside the event horizon. She asked the nearby stars to reveal what they were orbiting. That is the deep strength of orbital astronomy. Gravity does not need permission to leave evidence. If a hidden mass governs motion, then motion becomes the record. The recognition in 2020 made that logic public on the largest stage. The Nobel Prize in Physics was divided so that one half honored Roger Penrose for showing that black hole formation follows robustly from general relativity, while the other half was shared by Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. The press release and summary both emphasize that Genzel and Ghez found an invisible and extremely heavy object governing stellar orbits at the galactic center. That wording is worth dwelling on because it is careful. The Nobel language says, supermassive compact object, then adds that a supermassive black hole is the only currently known explanation. This is scientific writing at its best. It respects the chain from measurement to interpretation. The observation is that stars move around an unseen mass. The inference is that the mass is compact and enormous. The physical explanation that fits all of it is a supermassive black hole. The human side of the achievement also matters. This was not a discovery made by glancing once through a telescope. It required decades of attention to the same patch of sky, improvements in imaging, improvements in infrared observing, repeated measurement, and the discipline to let the orbits accumulate enough weight to speak clearly. UCLA states that Ghez had been collecting galactic center data for more than 23 years. That long baseline is one reason the result feels so strong. The evidence did not flash and vanish. It returned, orbit after orbit. The result also changed how many people imagine proof in astronomy. Proof does not always mean a direct photograph of the hidden object. In many areas of physics and astronomy, proof comes from constraints so tight that alternatives stop making sense. At the center of the Milky Way, stars were racing around an invisible mass of roughly 4 million suns packed into a remarkably small volume. No ordinary star cluster could remain stable under those conditions for long. No diffuse cloud could produce those orbits. The gravitational center was dark, compact, and immense. That is why this story sits so firmly within black hole astronomy as a whole. Earlier parts of this series have dealt with invisible objects, accretion disks, and gravitational lensing. Here the evidence came from orbital mechanics. The black hole did not need to feed on gas or flare in X-rays to be exposed. Its gravity alone, acting over years and decades, forced the nearby stars to trace out the hidden mass at the Milky Way's core. Seen from far away, the center of the Milky Way looks like a bright, crowded bulge crossed by dark dust lanes. But through the measurements made by Andrea Ghez and her collaborators, it becomes something much more exact. It is a region where stellar motion has been tracked carefully enough to weigh an invisible object and show that the heart of our galaxy contains a compact mass of about 4 million suns. That is how a hidden black hole was established without ever being seen directly. And once that invisible mass is accepted, attention moves to the boundary that gives a black hole its most decisive property. What happens at the event horizon, and why does that line change everything? The event horizon matters because it is the place where the rules of escape stop working. Not because a wall suddenly appears. Not because matter hits a hard shell. NASA describes the event horizon as a boundary, not a surface like Earth's ground or the Sun's visible face. It is the limit around a black hole beyond which nothing can get back out, including light. That distinction is the whole heart of the subject. When people first hear about black holes, many imagine something like a cosmic vacuum cleaner that grabs light and drags it inward by brute force. General relativity gives a deeper picture. Gravity is not treated as an invisible rope pulling across empty space. It is the geometry of space-time itself. Near a black hole, that geometry is curved so severely that beyond a certain boundary, every possible outward route is gone. The light is not trying hard and failing. The structure of space-time no longer offers it a path that leads back out. This is why the line changes everything. Outside the event horizon, light can still move away if it is emitted in the right direction. Its path may be bent. It may be redshifted. It may loop or scatter. But escape is still part of the menu of possible futures. Inside the horizon, escape is no longer one of the available options. NASA's educational material puts it in plain terms. Matter and radiation fall in, but they cannot get out. A useful way to approach this is through escape velocity, as long as we do not stop there. ESA explains that every object in space has an escape velocity, the speed needed to break free of its gravity. On Earth, that value is about 11 kilometers per second. At the event horizon of a black hole, the required escape speed reaches the speed of light. Since nothing can outrun light, and light itself is already the maximum speed allowed by relativity, the consequence is immediate. Once inside that boundary, nothing can escape outward. But the event horizon is more than an escape velocity slogan. The deeper physical meaning is causal. In relativity, the important issue is not merely how fast something is moving, but what future directions are physically possible. One ESA black hole white paper states this very directly. A horizon is a causal boundary, and fields there satisfy purely ingoing conditions. That language sounds technical, but the meaning is concrete. Once a signal is inside the horizon, every allowed future path points further inward rather than outward toward the rest of the universe. That is why the event horizon is often called the point of no return. Britannica defines it as the boundary marking the limits of a black hole, where the escape velocity equals the speed of light. NASA's Jet Propulsion Laboratory says much the same in educational material on Sagittarius A star. The event horizon is the spherical boundary where the velocity needed to escape exceeds the speed of light. There is also something important the event horizon is not. It is not the central singularity. It is not the place where density becomes formally infinite in the classical equations. The horizon is farther out. It is the boundary that separates the exterior region, where information can still in principle reach distant observers, from the interior region, where it cannot. NASA Glenn's educational page describes the event horizon as the divider between two disjoint regions, the outside universe and the black hole interior. That separation is why black holes can influence their surroundings so strongly while still hiding their interiors completely. Gas can orbit outside the horizon. Magnetic fields can twist outside the horizon. Accretion disks can blaze outside the horizon. Light can be bent outside the horizon. But once matter or radiation crosses inward, the outside universe loses access to it. This is exactly why black holes can be studied by their effects on nearby matter and light, even though the defining region remains hidden. The Event Horizon Telescope helped make this distinction more intuitive. The telescope was named after the event horizon, but the famous images of M87 star and Sagittarius A star are not photographs of the hidden interior. They are images of glowing material outside the black hole, together with the dark central shadow caused by strong gravity bending and capturing light near the horizon. That point matters here because it shows what astronomers can and cannot observe. They can study the edge region. They can infer the geometry. They can test whether the shadow size matches general relativity. But they do not watch signals emerge from inside the horizon, because the horizon is defined by the impossibility of such return. Another common misunderstanding is that an astronaut would necessarily slam into something solid at the event horizon. In the standard relativity picture, the horizon itself is not a material crust. NASA says plainly that it is not a surface like Earth's or the Sun's. For a very large black hole, the tidal forces right at the horizon can actually be modest enough that, in principle, crossing that boundary would not feel like striking a wall at that exact location. The fatal physics comes from deeper in, where gravity's variation across the body becomes extreme. So, the event horizon changes everything for information and causality, even though it is not, in the ordinary sense, a visible or touchable surface. This last sentence is an inference from the standard general relativistic description of the horizon as a boundary rather than a material surface. Time also behaves differently near this boundary, depending on who is doing the observing. To a distant observer, clocks near a black hole appear to run more slowly because of gravitational time dilation. That is one reason popular accounts often say an infalling object seems to freeze near the horizon. Britannica's recent explainer notes that time slows dramatically at the edge of a black hole. The careful version is this: for distant observers using signals sent outward, the object appears increasingly redshifted and harder to see as it approaches the horizon. For the falling object itself, the experience is different. Crossing the horizon is not marked by a visible sign that says, "now." The horizon is therefore a geometric and causal boundary first of all, not a glowing line painted onto space. This comparison between outside and infalling viewpoints is an inference from general relativity's treatment of horizons and redshift. Once that is understood, the black hole stops looking like a monster that reaches out and starts looking like a region where space-time has been curved into a one-way structure. NASA's Black Hole Overview says that just beneath the event horizon gravity is strong enough that nothing can escape. The phrasing, "just beneath its surface," can tempt people back toward the image of a physical shell, but NASA immediately clarifies that the event horizon is a boundary, not a conventional surface. The line changes everything because physics outside and inside it are connected in a very unequal way. Outside the black hole, events can still influence the wider universe. Inside, they cannot send any new message back out. JPL's No Escape teaching material says no information about events occurring inside the event horizon is available to the rest of the universe. That is not just a detail. It is the reason black holes create such deep puzzles about information, entropy, and quantum theory. Once information crosses that line, classical general relativity says the outside world loses direct access to it. That final sentence is a high-level inference from the horizon's role as a causal boundary and from the standard information problem in black hole physics. It also explains why the event horizon, rather than the singularity, dominates actual astronomy. Telescopes cannot study the singularity directly. Even classically, the singularity is hidden behind the horizon. What observers can test is the outer geometry, the orbits of stars, the heating of accretion disks, the bending of light, the shadow size, the polarization of plasma near the edge. So what happens at the event horizon? In the clearest physical sense, the set of possible futures changes. Outside the line, outward communication still exists in principle. At the line, even a light beam aimed outward no longer gains a clear route away. Inside the line, even light has no outward path left. That is why the black hole does not need to behave like a vacuum cleaner grabbing beams of light by force. Space-time has already been curved so severely that return paths stop existing. Why doesn't a black hole need to touch light to make it vanish? A black hole does not need to reach out and grab light like a hand closing around a beam. That picture feels natural at first, but it is not how the physics works. In general relativity, light moves through space-time by following the geometry available to it. Britannica summarizes the core idea clearly. Gravity in Einstein's theory arises from the shape of space-time itself, not from a force acting in the old Newtonian sense. So near a black hole, light is not being pulled aside by contact. It is moving along paths inside a region where space-time has been curved into a far more severe shape than anything we meet around planets or ordinary stars. That is why a black hole can bend light into arcs, rings, and finally lost from view while still remaining dark at its center. NASA explains that massive objects like black holes can bend and distort light from more distant sources, an effect called gravitational lensing. The Event Horizon Telescope gives the same idea in more specific language for black holes. Photons emitted by gas falling inward should travel along curved trajectories and form a ring of light around a shadow. Those two descriptions fit together neatly. Far from the black hole, the bending may produce lensing of background objects. Closer in, the bending becomes so strong that some light loops around the hole, some escapes after extreme deflection, and some never returns to the outside universe at all. This is the elegant part of the story. Light always travels at the speed of light in its local environment, but the route it takes depends on the geometry of space-time. A black hole does not make light slow down and surrender. It changes the structure through which light must move. Britannica's description of gravitational lensing says matter alters the direction of light, passing nearby through the bending of space in its gravitational field. That sentence is already enough to explain the first step. Once the curvature is modest, the light bends a little. Once the curvature is extreme, the bending becomes dramatic. A black hole is the limiting case where the geometry becomes so severe that beyond the event horizon, outward light paths are no longer available at all. That is also why the center stays dark, even when the surroundings are bright. The ring in black hole images is not a glowing edge of the hidden interior. The Event Horizon Telescope says the expected picture is a ring of light around a shadow because photons from infalling gas follow curved trajectories near the black hole. In other words, the bright structures come from hot gas outside the event horizon, while the dark central region marks where light paths have been removed from our view by gravity. The black hole does not need to emit darkness. It only needs to prevent certain light rays from reaching us. Once you frame it that way, gravitational lensing and black hole invisibility stop looking like separate topics. They are two expressions of the same underlying geometry. NASA notes that gravitational lensing can even be used to find isolated black holes that are otherwise invisible. That means the same space-time curvature that hides the interior can also betray the object's existence by reshaping the light of something behind it. An unseen black hole can briefly magnify a background star, distort its apparent position, or produce more complex warped views in simulations. The darkness and the distortion come from the same source. NASA visualizations make this easier to picture because they show how strong black hole gravity can create multiple warped images of nearby bright material. In one NASA visualization of a black hole pair, bright hot disks around the black holes are distorted into repeated, increasingly warped images by the curvature of space-time. The important lesson is not the beauty of the visual alone. It is the physical principle underneath it. Light does not need to strike the black hole head-on to be affected. The geometry surrounding the hole already guides the light into new trajectories long before any ray approaches the event horizon itself. There is a useful sequence hidden inside this. First, at large distances, a black hole acts as a gravitational lens, bending light by a measurable amount. Second, closer in, the bending becomes strong enough to produce arcs, rings, and repeated images. Third, near the edge, some photons can circle or nearly circle the hole before escaping. Fourth, beyond the event horizon, escape stops being part of the future at all. The Event Horizon Telescope's science summary compresses that whole ladder into one sentence when it says photons travel along curved trajectories and form a ring of light around a shadow. That sentence contains an enormous amount of geometry. This is where John Archibald Wheeler enters the story in an important way. Physics often reaches a point where the mathematics is known before the language becomes stable enough for people to hold on to the idea clearly. Princeton's Department of Physics describes Wheeler as the physicist who coined the term black hole, and Princeton's historical notes on relativity state that Karl Schwarzschild found the extreme gravity, solutions decades earlier, which Wheeler later renamed black holes. That naming mattered. A compressed phrase gave scientists and the public a way to talk about an object whose defining feature was not brightness, surface, or color, but a region where light itself could be prevented from returning. Wheeler's role mattered for another reason too. Princeton notes that he helped rejuvenate interest in general relativity, and Princeton's coverage of Kip Thorne's Nobel recognition says Wheeler added both black hole and wormhole to the scientific lexicon. That means Wheeler did not merely supply a catchy label. He helped shape the modern language physicists use to describe extreme spacetime. Once the term black hole entered common use, the subject became easier to discuss as a concrete physical entity rather than as a cumbersome mathematical oddity from Einstein's equations. That language matters here because the phrase black hole can mislead if taken too literally. It is not a hole in the sense of an empty tunnel punched through space. It is a region where the geometry of space-time has been deformed so strongly that the future of anything crossing the horizon leads inward. The center appears black, not because the object paints itself black, but because light that would have informed us about the interior does not reach us. Britannica's General Relativity Overview and NASA's black hole materials line up on this point from different angles. One emphasizes geometric gravity. The other emphasizes the observational consequence that light cannot escape. That same geometry is why black holes can produce some of the most extreme lensing in the universe. A galaxy cluster can lens background galaxies into stretched arcs because of its enormous mass spread over a vast region. A black hole can do something more concentrated. Near it, light can be bent so dramatically that emission from nearby gas can wrap into a ring-like appearance and background structure can be multiplied or heavily warped. NASA's Inside a Black Hole discussion describes light from a star traveling through warped space around a black hole and appearing strange, even donut-like. The central darkness remains because the black hole still withholds direct escape from within the horizon. One of the most useful things about this explanation is that it removes the need for a misleading image of physical contact. A black hole does not need to touch light to make it vanish, because vanishing, in this context, means the light never reaches the observer. A beam may be bent away. It may be captured. It may circle and then fall inward. From our perspective, The result is missing information. The light did not have to collide with a hard object to disappear from view. It only had to follow the geometry that no longer leads back to us. This also explains why black hole astronomy depends so much on inference from surrounding light. If the object itself prevents direct signals from inside the horizon from reaching us, then the measurements have to come from what remains outside: hot gas, polarized emission, lensing of background light, and the motions of nearby stars. NASA's Black Hole Overview emphasizes that black holes are studied through their effects on nearby matter and light, while the Event Horizon Telescope shows that those effects extend right down to horizon-scale rings and shadows. The dark center and the distorted light around it are not separate stories. They are the same geometry written in two different ways. So why doesn't a black hole need to touch light to make it vanish? Because light is always following the structure of space-time, and near a black hole space-time itself has become the trap. John Archibald Wheeler helped give that strange reality a name people could remember. Modern observatories have since turned it into measurable evidence, from shadow images and lensing signals to precise tests of general relativity. The result is one of the clearest lessons in all of physics. What disappears from view is not always what has been destroyed. Sometimes it has simply entered a geometry from which return no longer exists. If black holes are truly invisible, how did humanity hear two of them collide in 2015? On September 14, 2015, humanity detected something it had never detected before. Not a flash of ordinary light. Not an X-ray burst. Not a radio flare from a black hole feeding on gas. What LIGO measured was a ripple in space-time itself, arriving at Earth after a journey of more than 1 billion years. The event is now known as GW150914, and LIGO described it as the first direct detection of gravitational waves and also the first observation of a binary black hole merger. That is why this moment felt so different from everything that came before. Until then, black holes had been inferred through X-rays, stellar orbits, jets, and lensing. In this case, two invisible objects announced themselves through gravity alone. The timing of the signal is now one of the fixed points in modern astronomy. LIGO states that the twin detectors in Livingston, Louisiana, and Hanford, Washington, recorded the event on September 14, 2015, at about 9:51 UTC. The two observatories saw the signal in both instruments, which mattered enormously because a real gravitational wave event should cross both detectors with the right delay and structure, while a local disturbance at one site should not. The signal itself lasted only about 0.2 of a second, yet that brief interval carried enough information to show that two compact, massive objects had spiraled together and merged. What made the signal so persuasive was its shape. As the two objects orbited closer and closer, the measured waveform rose in frequency and amplitude, the famous chirp pattern predicted by general relativity for inspiraling compact bodies. Then came the merger itself, followed by the final settling of the newly formed black hole, often called the ringdown. Nobel lecture material from Kip Thorne describes that final stage as a distorted merged black hole that vibrates briefly and emits gravitational waves, like a damped bell losing its last energy. So the first detection was not just a spike in noise. It carried the three-part physical story of inspiral, merger, and ringdown, all packed into a waveform. From that waveform, physicists could estimate the masses of the colliding objects. The discovery paper reports source frame masses of about 36 and 29 solar masses. After the merger, the final black hole had a mass of about 62 suns, which means about 3 solar masses worth of energy was radiated away as gravitational waves. That number is one of the most arresting parts of the event. In a fraction of a second, an amount of energy comparable to converting 3 suns directly into radiation was carried across the universe in the form of space-time ripples. The Nobel Prize explanation repeats the same core result and notes that the 2 original black holes were each no larger than roughly 200 kilometers in diameter. That is the emotional turn at the center of this story. Black holes did not become visible in the ordinary sense. The universe did not suddenly switch on a lamp inside them. Instead, their motion shook space-time strongly enough for Earth to register the disturbance. LIGO's press release says gravitational waves carry information about dramatic origins and about the nature of gravity that cannot otherwise be obtained. That phrase matters because it explains why GW150914 was not simply one more black hole observation. It opened a different channel of astronomy. The message no longer had to ride on light. To understand why this was possible, it helps to stay close to Einstein's original idea. In general relativity, accelerating masses can create ripples in space-time, much as moving charges create electromagnetic radiation. Most motions in the universe produce gravitational waves too weak to detect. But 2 black holes, orbiting each other at high speed, with tens of solar masses packed into small regions, create conditions extreme enough for the effect to rise into measurability. By the last moments before merger, the orbit tightens, the speed rises, and the gravitational wave emission becomes much stronger. The signal that reached Earth was therefore the final loud phase of a long in-spiral. This causal explanation is an inference from the LIGO waveform interpretation and the standard in-spiral merger ring-down model described in LIGO and Nobel materials. The distance makes the detection even more impressive. The discovery paper places the source at roughly 400 megaparsecs, while LIGO's science summary describes it as coming from more than 1 billion light-years away. That means the disturbance reaching Earth was incredibly small by the time it arrived. Yet advanced LIGO was sensitive enough to register it. LIGO's own materials describe the observatories as among the most sensitive scientific instruments ever built, and that is not a flourish. The signal from GW150914 was tiny, but it was patterned, synchronized, and physically meaningful. The event also changed what astronomers knew about black holes themselves. Before GW150914, stellar mass black holes had often been identified in X-ray binaries, where matter falling in from a companion star made them easier to notice. GW150914 showed that there exist binary systems of 2 black holes, each with unexpectedly high stellar masses, merging in the distant universe. The discovery paper states that these observations demonstrate the existence of binary stellar mass black hole systems. That was a major astrophysical result in its own right. It meant the universe had been building pairs of black holes, letting them survive, tightening their orbits, and finally driving them together. There is a reason people often say humanity heard the collision. The LIGO data can be converted into an audio-like signal because the frequencies of the detected waves pass through the human hearing range during the final chirp. That wording is not literal in the sense of sound traveling through space like air vibrations. Space between the black holes was silent in the ordinary acoustic sense. What reached Earth was a variation in spacetime measured by laser interferometers. But once translated into sound for human ears, the signal compresses an enormous cosmic event into a brief rising tone. That made the discovery emotionally immediate in a way few graphs ever do. This explanation is an inference from the nature of the LIGO waveform and the common sonification practice. The underlying measured quantity remained gravitational strain, not sound in a medium. The violence of the merger is easy to underestimate because the signal was brief. LIGO's science summary reports that the peak gravitational wave power in the final moments exceeded the combined light power from all the stars in the observable universe. That does not mean the event outshone the universe in visible light. It means the instantaneous power emitted in gravitational waves at peak was astonishingly large. This is one of those numbers that changes scale in the mind. Two dark objects, invisible in ordinary light, briefly outperformed the luminous cosmos in a completely different channel of radiation. GW150914 also mattered because it tested general relativity in a regime that had never been probed directly before. Einstein's theory had already passed many tests in weak and moderate gravitational fields. What LIGO captured was the strong field, highly dynamical regime of two black holes colliding and settling into one. The observed waveform matched the predictions of relativity for such a merger, and the Nobel Prize documents describe the discovery as confirming predictions of the general theory of relativity, while also opening a new way to study black holes. This is why the discovery feels like more than a technical triumph. It changed the answer to a basic human limitation. For centuries, astronomy meant reading light. Then, in 2015, an invisible system far away announced itself through gravity. The black holes were still black. No ordinary image showed their interiors, but the collision imprinted a measurable shape onto spacetime, and Earth was finally able to register it. LIGO's press materials say gravitational waves carry information that cannot otherwise be obtained, and GW150914 proved that statement in one stroke. Seen this way, the first detection did not contradict black hole invisibility. It revealed it in a new form. We did not see the black holes in the usual way. We detected what their gravity did when two of them spiraled together and rearranged space-time itself. On September 14, 2015, an object that gives off no visible light still left a signal strong enough to cross the universe and reach human instruments. It spoke not in color or brightness, but in a ripple written into the structure of space-time. Why is our own supermassive black hole so faint when it is 4 million suns heavy? At the center of the Milky Way sits an object with a mass of about 4 million suns, and yet by the standards of active galactic nuclei, it is strangely subdued. That contrast is one of the most revealing features of Sagittarius A star. NASA describes it as the supermassive black hole at our galaxy's center, with a mass of about 4.3 million times that of the Sun, but far less luminous than the blazing central engines seen in many other galaxies. So the mystery is not whether the Milky Way has a central black hole. That has been established through stellar orbits and later horizon-scale imaging. The more interesting issue is why something so massive is, at present, comparatively dim. The simplest part of the answer is that a black hole shines only when matter around it does. A black hole does not glow because of its mass alone. It becomes bright when gas falls inward, forms a hot accretion flow, and converts gravitational energy into radiation. NASA's ninth result on Sagittarius A says directly that our central black hole is much fainter than the actively feeding supermassive black holes in some other galaxies because it is currently consuming relatively little material. That one sentence removes a common misunderstanding. 4 million solar masses is enough to dominate the galactic center gravitationally, but not enough to guarantee a luminous display. Brightness depends on fuel supply and on how efficiently that fuel radiates before crossing the event horizon. That is why astronomers often compare Sagittarius A star with active galactic nuclei rather than with ordinary stars. In galaxies where the central black hole is swallowing large amounts of gas, the nucleus can outshine the rest of the galaxy and launch jets or winds across enormous distances. Our galaxy is not in that state today. NASA's description of Sagittarius A star through ninths says the Milky Way's central black hole is fainter than most supermassive black holes and behaves more like a quiet engine than a blazing one, even though it still produces variable emission and occasional flares. So the faintness is relative, not absolute. Sagittarius A star is quiet by the standards of the brightest galactic nuclei, but it is not completely inactive. That distinction becomes clearer when you look at the flares. Chandra reported in 2012 that Sagittarius A star produces X-ray flares about once a day, lasting a few hours, with brightness ranging from a few times up to nearly 100 times its regular output. Those flares were also seen in infrared data from ESO's Very Large Telescope. This matters because it shows that the central black hole is not sitting in perfect stillness. Gas does reach it from time to time. Magnetic fields do reorganize. Energy does get released in bursts. The picture is therefore not one of absence, but of low average feeding, punctuated by brief activity. Modern horizon scale observing sharpened that picture further. The Event Horizon Telescope results for Sagittarius A star showed that the source is variable on short timescales, one reason it was harder to image cleanly than M87 star. EHT materials explain that gas around Sagittarius A star changes on timescales of minutes, whereas the flow around the much more massive black hole in M87 changes more slowly. So our central black hole is faint overall, but its immediate surroundings are restless. The source flickers. The emission pattern changes rapidly. That is an important correction to the phrase quiet black hole. Quiet does not mean frozen. It means low average luminosity compared with the great active nuclei of the universe. NASA's ninth PE work adds another layer because it probes polarization in X-rays, which carries information about magnetic fields and geometry near the black hole. In that result, NASA concluded that the X-ray polarization suggests hot material near Sagittarius A star is organized by strong magnetic fields, and the same basic magnetic field geometry may help explain both our black hole's current faintness and its ability to produce sporadic flares. In other words, the faintness is not merely about having less gas. It is also about what happens to the gas that is present, how it flows, how it heats, how much of its energy escapes as radiation, and how much falls inward without radiating efficiently. That phrase, "without radiating efficiently," is a major part of the physics. Many models of Sagittarius A star treat it as a radiatively inefficient accretion flow. The basic idea is that much of the energy in the inflowing gas does not emerge as bright light before the gas disappears inward or is carried away in outflows. NASA's 9th summary does not use that exact phrase in the headline, but the result points in that direction by emphasizing weak feeding, hot plasma, and magnetic structure. The faintness of Sagittarius A star is therefore not surprising once accretion physics is included. A giant black hole can remain dim if the gas supply is thin, and if the conversion of gravitational energy into escaping radiation is inefficient. This last sentence is an inference from the NASA 9's interpretation and the standard low accretion model for Sagittarius, a star. And yet, the story does not settle into calm for long, because there is evidence that Sagittarius A star was more active in the recent past. Chandra has been building that case for years through X-ray echoes in molecular clouds near the galactic center. In 2007, Chandra reported evidence for a light echo suggesting that Sagittarius A star had devoured matter and produced an X-ray outburst decades earlier. In 2008, Chandra described signs that the central black hole had awakened from slumber about 300 years ago, with X-ray pulses illuminating the cloud Sagittarius B2. In 2013, Chandra reported evidence for two distinct past flares recorded as X-ray echoes. And in January 2025, Chandra said, "New work on molecular clouds helped reconstruct the three-dimensional structure of the region, precisely because past X-ray flares from Sagittarius A star had propagated outward and lit up those clouds. This is where the subject becomes especially compelling. The black hole looks faint today, but the surrounding clouds remember brighter episodes. That is why invisibility here feels less like emptiness and more like restraint. The central engine is capable of stronger output. It simply is not operating at that level right now." Chandra's light echo pages describe these clouds as recording earlier eruptions, almost like delayed reflections of behavior we no longer see directly. The galactic center, then, is not a static environment. It is a region where present quietness coexists with evidence for past agitation. NASA has even given a more specific recent estimate for one such bright episode. In a 2023 NICE-related release, NASA said the Milky Way's central black hole appears to have woke up around 200 years ago, based on polarized X-ray echoes seen from nearby clouds. That does not mean the black hole entered a quasar-like phase visible across the universe. It means that on the scale of Sagittarius A star's usual present-day faintness, it underwent a stronger feeding event whose radiation still left a trace in the environment. The clouds around the galactic center function as delayed witnesses. That mix of restraint and variability also fits with everyday flare monitoring. Chandra's earlier reports emphasized that Sagittarius A star shows regular X-ray flares lasting hours, while EHT observations and later ULMA planning documents describe it as a source with intra-hour variability and daily flares. So the current Milky Way black hole is not simply asleep. It is better described as underfed, magnetically active, and intermittently restless. This matters because a black hole's visibility is governed not only by mass, but by the physical state of matter near it at a given time. The broader galactic center environment strengthens this picture. Chandra's January 2025 release describes the central region of the Milky Way as an extreme environment where gas temperatures, densities, and turbulence are about 10 times higher than in the rest of the galaxy. That means there is material available, but feeding the black hole is not a simple, steady funnel. Gas has to lose angular momentum, move through a chaotic environment, and survive complex magnetic and turbulent processes before it can be swallowed efficiently. A 4 million solar mass black hole can therefore remain faint not because nothing is nearby, but because getting matter all the way in is harder than the raw mass figure might suggest. So why is our own supermassive black hole so faint when it is 4 million suns heavy? Because mass sets the gravitational stage, but luminosity depends on feeding. Sagittarius A star is not surrounded by the steady, dense inflow of matter needed to power a brilliant active nucleus, and the gas that does fall inward appears to radiate inefficiently. Even so, it still produces X-ray and infrared flares, and X-ray echoes in nearby clouds suggest that it was more active in the recent past. That makes the galactic center useful in a special way. The darkness there is real, but it is not a sign of inactivity. It is the signature of a powerful gravitational system operating most of the time in a low luminosity state. Are black holes invisible because physics itself breaks at their edge? Black holes are invisible in more than one sense. Telescopes cannot look inside the event horizon because no light from within that boundary can return to us. But there is a second layer that runs deeper than observation. General relativity explains with remarkable success why a black hole traps light, curves space-time, and shapes the motion of matter around it. At the same time, the theory points toward regions where its own classical description is no longer enough. The Nobel Prize materials for 2020 put this very clearly. Roger Penrose showed that black holes are a direct consequence of general relativity, yet at the singularity, the known laws of nature cease to apply, and theoretical physics still seeks a theory of quantum gravity that can unite relativity with quantum mechanics. That distinction matters because it keeps two different claims from being mixed together. General relativity is not failing in ordinary black hole astronomy. On the contrary, it has been extraordinarily successful. It explains why the event horizon is a no-return boundary, why light is bent near compact masses, why stars can orbit an unseen object at the center of the Milky Way, and why merging black holes produce gravitational waves. NASA explains that any light detected by telescopes is not from the black hole itself, but from the area surrounding it, and that the inner edge of that visible region is the event horizon. The Nobel Committee likewise states that black holes emerge naturally from Einstein's theory. So, in one very important sense, physics does not break at the edge of a black hole. The edge is exactly where a great deal of black hole physics works extremely well. The Event Horizon Telescope, LIGO, stellar orbit measurements near Sagittarius A star, and X-ray observations of accretion flows all rely on the fact that the outer gravitational structure of black holes is mathematically stable and observationally testable. NASA's recent Physics of the Cosmos overview even emphasizes that some of the best tests of gravity come in the most extreme conditions near black hole event horizons and in close black hole interactions. That is a strong statement. It means black holes are not just places where theory becomes vague. They are also among the sharpest laboratories we have for checking whether our best theory of gravity holds up under stress. The trouble begins when the description is pushed all the way inward. Penrose's work showed that under broad conditions, gravitational collapse leads to singularities in general relativity. The Nobel material says that at the heart of a black hole lies a singularity, where all known laws of nature break down. That does not mean physicists have a full observational map of a physical point called the singularity. It means the classical equations drive us toward a regime where quantities blow up and the theory stops giving a complete physical account. In that sense, the invisible interior of a black hole is also partly invisible to our final understanding. This is exactly why quantum gravity enters the story. General relativity is a classical theory of space-time. Quantum mechanics governs the microscopic world with astonishing accuracy. Black holes force those two frameworks into the same room. The Nobel explanation says theoretical physics is still trying to create a theory of quantum gravity that unites these two pillars because they meet in the extreme interior of black holes. That line is one of the clearest summaries of the modern problem. We know a great deal about how gravity behaves on large scales and a great deal about quantum physics on small scales, but we do not yet have a completed theory that fully explains a black hole all the way down. Stephen Hawking made that problem even harder and much more interesting. In 1974, he proposed that black holes are not completely black when quantum effects are taken into account, but emit thermal radiation. Nature's summary of that work states that Hawking suggested black holes emit radiation with a temperature that depends on their mass. This changed the subject completely because it meant black holes were no longer just one-way sinks in a purely classical sense. They could, in principle, lose mass and eventually evaporate. Once that idea was added, a deeper puzzle appeared. What happens to the information about everything that fell in? That puzzle is now one of the most famous unresolved problems in theoretical physics. The American Physical Society describes the black hole information paradox as one of the greatest unsolved mysteries of theoretical physics, arising from the tension between semi-classical gravity and the requirement in quantum mechanics that information is not destroyed. Another APS source states the paradox is a conflict between quantum mechanics and general relativity. This is why black holes remain unsolved even after so many spectacular observational successes. We can measure their masses. We can image their shadows. We can detect their mergers. But we still do not fully know how gravity, quantum theory, information, and space-time fit together in the most extreme black hole regime. It is important to keep the boundary of certainty clear here. We are not in a situation where black holes are mysterious because we know almost nothing about them. That would be the wrong impression. We know enough to say with confidence that black holes form, that event horizons exist in the general relativistic description, that light from inside cannot escape, that supermassive black holes inhabit galactic centers, and that black hole mergers produce gravitational waves. The unresolved part is more specific and more demanding. It concerns the ultimate microscopic description of space-time, the fate of information, and the quantum structure of horizons and interiors. That is what makes the title of this final part worth answering carefully. Are black holes invisible because physics itself breaks at their edge? Not in the ordinary observational sense. The event horizon is not a place where all physics suddenly becomes useless. It is a place where general relativity gives a strong and predictive account of no-return geometry. But black holes do point toward a limit of our present frameworks, because the same theory that explains their outer structure also predicts singular behavior deeper in, and quantum theory suggests additional effects such as Hawking radiation that classical gravity alone cannot finish explaining. There is something almost severe about that balance. Black holes are not hidden only because they refuse to emit light from within the horizon. They are also hidden because nature has placed one of its deepest unfinished problems there. Telescopes can push closer to the edge. Gravitational wave detectors can hear mergers. Horizon-scale imaging can sharpen the geometry. Yet the final union of gravity and quantum physics remains incomplete. NASA's black hole materials explain why black holes appear black to telescopes. The Nobel materials explain why singularities reveal the limit of the known laws. APS explains why the information paradox remains open. Put together, those three threads show why black holes remain some of the most compelling objects in all of science. That is also why black holes never settled into being just another solved chapter of astronomy. Each decade has made them more real, not less. Penrose proved that gravitational collapse can produce them. Andrea Ghez and Reinhard Genzel helped show that one governs the center of our galaxy. The Event Horizon Telescope mapped horizon-scale structure around M87 star and Sagittarius A star. LIGO detected black holes merging through gravitational waves. The more evidence arrived, the more clearly black holes stood at the meeting point of our strongest successes and our deepest unfinished work. And that is where this journey comes to rest. Black holes are invisible because light cannot escape their interior. They are also invisible in a second way, because the final theory that should describe their deepest structure has not yet been completed. We can trace their shadows, measure their gravity, hear their mergers, and model their surroundings with impressive precision. Yet, the last layer, the full reconciliation of space-time and quantum law, still waits. That unfinished edge is part of what gives black holes their hold on modern physics. They are not simply dark objects in space. They are places where knowledge becomes sharp, then incomplete, then urgently alive again. If you have stayed with me all the way to the end of this long exploration, thank you. I truly appreciate your time, your attention, and your trust in these science stories. A like or a quiet tap on subscribe is a real source of encouragement for me to keep making them, one by one. And if you would like, share where you are listening from and tell me what part of the universe you would like us to visit next. I hope tonight brings you good rest, a steady mind, and a peaceful sleep. Good night.